Here we discuss about a project AES-GCM and AEGIS, an efficient and high-speed hardware implementation. Here, the authenticated encryption is become an essential part of modern secure communication system, including Internet of Things devices, wireless network, cloud storage, and embedded application, and high-speed data transmission performance. This system requires both confidentiality and authentication to ensure secure and reliable communication. Among the available authenticated encryption technique, AES-GCM has gained a significant authentication because of its high security, low latency, and parallel processing capability. However, the GHASH model in AES-GCM introduced a high computational complexity and critical path delay due to the GF of 2 power 128 multiplication process, which reduces the overall throughput and hardware efficiency in FPGA implementation. The existing architecture mainly focuses on conventional Karatsuba Ofman Algorithm based GHASH structure and pipeline multiplier, but they still suffers from XOR overlap delay, authentication bottleneck, and higher propagation in recursive multiplication stages. To address this limitation, this work proposes a high-speed AES-GCM authenticated encryption architecture using a 128-bit overlap-free Karatsuba GF multiplication technique together with a parallel KOA GHASH controller for efficient authenticated processing. The proposed architectures also integrated a carry lookahead adder to reduce arithmetic propagation delay in both AES and multiplier data path. In this work, the 512-bit plaintext data is proposed using 4 segment of AES 128-bit encryption operation to improve a multi-block encryption efficiency. The major novelty of the proposed work is the integrations of overlap-free Karatsuba multiplication, parallel GHASH scheduling algorithm, and CLA-assisted data path optimization into unified FPGA-based AES-GCM architecture for reduced critical path and improved throughput performance. The complete architecture was designed using Verilog HDL and synthesized using Xilinx Virtex-5 targeting AES Artix-7 FPGA, and performance evaluations was carried out based on LUT utilization, timing analysis, operating frequency, throughput, and hardware efficiency, where the proposed architectures achieved a high-speed operation 400 MHz with improved timing performance compared with the conventional Karatsuba-based AES-GCM implementation. Now we can verify this paper. So this paper presents with the AES-GCM architecture. Okay, so here the figure 1 architectures, it will be shows the overall system architecture of AES algorithm with the GCM. Okay, so here the total plain text, it will be covered with 512-bit. So depends upon the requirement, we can choose a multiple number of bits. Okay, so here for our purpose we choose a 512-bit, and the 4 AES 128-bit architectures internally we used in this architectures. Okay, so that architectures, it will be covered with a 4 times in parallel. Okay, so here to improve the performance of encryptions, the GF multipliers, it will be used with a technique of KOA GHASH parallel architecture of Karatsuba multiplications. Okay, for Karatsuba multiplication we have used this paper. So this paper presents with an efficient and high-speed overlap-free Karatsuba based finite field multiplier for FPGA implementation. So here we use these 2 architectures. Okay, the figure 2 is a standard architecture and figure 3 is overlap-free Karatsuba architecture. Okay, so the both it will be covered, but we have designed this architectures at 128-bit method. Okay, so this architectures they given in 4-bit architectures only. Okay, and the proposed architecture of parallel method, it will be used in figure 6 architectures. Okay, so here it will be covered with the sequential technique method. Okay, so the 4 parallel architectures means Okay, so one by one of AES architectures it will be used. Okay, so in 4 parallel architectures they will take a more logic size and more power consumptions and more number of LUTs, LUT RAM, flip-flops, everything it will be taken. Okay, so for one by one of sequence of AES-GCM method, it will be reduced the number of logic size, power consumptions and everything. Okay, so for the purpose this proposed architecture will be helpful. Okay, so here this is a method. Okay, the AES round key, round 1, round 2, round 3, this is a complete AES architecture. The key it will be given as an input, and the controlled input it will be come with the associated data, and the nonce also it will be given. Okay, and the plain text it will be exert it here. Okay, so once the first iterations it will be completed, then only we will get a H value, and that H value it will be used for the next iteration, and it will be come with a plain text XOR, and this proposed KOA based cache also it will be multiplied here, and we generated as a cipher text output. Okay, the same method, once you have understand this architectures, you will understand the proposed architectures easily. Okay, so here the first of all we need to generate the H value, and using that H value we need to multiply the A into H and the plain text 1 into H, cipher text 1 into H, and cipher text 2 into H, and cipher text n into H. Okay, finally we combine this all and it will be added with a MAC unit, and we taken as a final cipher architecture. Okay, so this work we have done in a Verilog HDL code with 2 different comparisons of overlap free and standard method, and this is a Karatsuba multiplications code of 128-bit. Okay, and this is a Verilog HDL code for standard method. Okay, and this is a Verilog HDL code for overlap free method. Okay, and this is a simulation result for Karatsuba multiplications. Okay, so here you can find the difference of overlap free and overlap method. Okay, for different random applications. Okay, so here the input it will be differ. Okay, so depend upon the input. Okay, so sometimes the overlap free and non overlap it will become with the same, and sometimes it will become with a different. Okay, so we use this architectures in the AES method. So this is a first standard method. Okay, so here we given a 512-bit input, so 511 down to 0 as a plain text. Okay, so here we have splitted the input data. Okay, so in the test bench it will be loading the data one by one into the plain text. Okay, so first of all we need to load the associated data, and the plain text 1, plain text 2, plain text 3, plain text 4. Okay, so here you can analyze it. So this is a AES-GCM input. Okay, so first of all we load this associated data, and the plain text 4 and plain text 3, plain text 2 and plain text 1 it will be loaded as a 4 sequence. Okay, and finally we covered with the AES encrypted data in here. Okay, so and then we started the second cycle and third cycle. Okay, so it's a n iterations it will be loading. Okay, and this is a overlap free architecture. Okay, so here you can analyze the plain text, associated data, GCM encryption, and AES done, and the plain text 1, 2, 3, 4, everything same, but the AES encryption's output only it will become with a different, depends upon the overlap free and standard method. Okay, so this architectures we have synthesized in Artix-7 in Vado. Okay, so here you can analyze the synthesis results. Okay, so this is the values LUT, LUT RAM, flip-flop, VRAM, IOB and BUFG architectures. Okay, so this is a delay and power consumption, and this is a proposed architecture of overlap free method. Okay, with the parallel to serial method of GHASH algorithm. Okay, so this is the architecture's performance, and this is a schematic. Okay, so here you can analyze this, the AES encryption 128-bit. Okay, so only one AES 128-bit we called it. So here this is a KOA cache and parallel cache controllers and carry local head data. Okay, so inside of this AES encryption, so AES key data and the encryption process it will be covered. Okay, and the parallel cache it will be come with this architecture, and KOA cache. Okay, so Karatsuba 128-bit multiplier, mod P 128-bit. Okay, and this is a Karatsuba. Actually 128-bit means we used 364 architecture. So, and inside of the 64 architecture we used KOA 32-bit. Okay, and instead of 32-bit we used Karatsuba 16-bit, and instead of 16-bit we used 8-bit and 4-bit and 2-bit, and finally the paper designed architecture. Okay. Okay, and this analysis we have written a comparisons table, and finally we have written abstract document for this project, base paper, improvement, proposed title, proposed abstract, and all the related notes. Okay, and finally come up with literature review and references. Thank you.
Are you planning to publish your next innovative research in IEEE transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.